Okay, welcome back. We're on page 69 looking at this figure 2.3, or table 2.3. And so this is the ASCII encoding scheme. And so is this good enough to send hello world? Yeah. But what about other languages? This ASCII setup was designed to break things down into one of 250 characters. Well, actually, originally it was 128. And then they just kept adding things onto the end. So there's 256 characters total in ASCII. But in a lot of, particularly in Oriental languages where you have special character sets, you need a couple thousand character combinations. And so this is clearly not good enough. And so they created yet another encoding scheme called Unicode. And Unicode was kind of designed to be sort of backwards compatible. It's sort of like starting with ASCII and then just adding on. Just making the ASCII characters bigger. Okay, that's kind of a dumb way of looking at it, but it works. So if I was to ask you what was the purpose for doing Unicode, you'd say, well, it's because if you have more than 256 characters, you can't use ASCII. Okay, on page 70, they talk about multiplexing. And so multiplexing is all about combining multiple signals. Now, I actually like this little photograph they have in the book. This is, circa 1900 or so, New York City. And so every single one of these wires is a single phone connection going through. And there's thousands of these things. And every phone company had to have their own. And so clearly something had to give. Because this is just not sustainable. You couldn't double this, for example. It wouldn't work. So the idea is that you want to be able to put more data on a single cable, guided media, whatever you want to call it. There's basically two different types of multiplexing. There's one called frequency division. So let's say, for example, I have a large bandwidth, and I'm using bandwidth in the right term, the right context now, a huge bandwidth. And so I carve up this for channel 1, and this for channel 2, this for channel 3, this for channel 4. I carve up my frequency. I divide my frequency division. And I can have multiple channels going on. And if my receivers are good enough, the receiver over here is not going to be interested in the data over here. Works. Kind of cool. So the other one is called time division. So time division is where everyone just gets a slot. So in other words, I'm using a kind of a narrow band, but you get the first, followed by you, gets the next packet, followed by you. And this is the way the packets work. Remember we talked about packet switching? Packet switching allows me to just interlace. So here's a conversation over here, here's a conversation over here, and they interlace in between each other. So I'm sending more data, more conversation, the multiplexing. So frequency division and time division. Time division, so frequency division is great for like cable TV, that kind of stuff, where I'm sending lots and lots of signals to your house. But if I'm sending Ethernet kind of internet traffic, I'm probably going to be using the time division. So they talk about the carrier frequency versus the signal one more time, and they show some diagrams of the carrier frequency, which is just the background waveform with no signal on it. And then they impose the signal, and so it distorts the waveform, and then it allows you to pull it back. Okay, so we've reached the end. I want you to go to page 75 and kind of look at the summary. Go through this. I'm not going to do it. You go through the summary yourself and make sure you got all the concepts. Okay, that's the end of this chapter, and we'll see you again in some future chapter.